Let's dive right into this explainer and discover how the exact same math used to figure out cafeteria lunch prices can actually be scaled up to model the entire economy of a country. Now, I know it sounds like a totally massive leap, right? But the underlying engine running both of these scenarios is exactly the same. By the end of our time today, you're going to see how a simple, unassuming grid of numbers holds the absolute key to understanding the wildly complex web of global industries.
So, here is our roadmap for today. First up, the magic of matrices. Then, solving the system. Third, modeling an entire economy. And finally, we'll wrap up with the input-output table.
All right, jumping right into part one, the magic of matrices. We're going to look at the foundational tools under the hood here. Think about this question for a second. When you're faced with multiple overlapping variables, say you're trying to balance the sales of $4, $5, and $6 cafeteria lunches based on total daily revenue and the exact number of items sold, we need a really reliable system to find the answer. If you just try to juggle all those equations in your head, human memory gets overloaded almost instantly. The mental gymnastics of tracking all those interacting constraints, it just becomes a tangled mess and you end up totally overwhelmed by the algebra. We literally need a way to organize all this chaos into something manageable.
And that brings us to our crucial mathematical tool, which essentially acts like a giant sandbox. An augmented matrix isolates the pure numbers from all those messy, confusing variables so we can manipulate them cleanly. You simply take the coefficients, the numbers directly attached to your variables, and neatly line them up on the left side of a vertical bar. Then you just drop your constants, like that total daily revenue, right on the right side. This visual separation provides a beautifully compact way to represent linear equations, giving us a super clean, highly structured workspace.
Now, here is what's actually really cool about this. These three simple elementary row operations are the only moves you are allowed to make. It's exactly like a board game with incredibly strict rules. You can swap any two rows, you can multiply or divide a whole row by any number, except 0, of course, because multiplying by 0 just destroys your information and isn't reversible. And finally, you can add a multiple of one row to another. By sticking strictly to these three specific moves, you prevent yourself from accidentally breaking the universe of our math problem. The mathematically guarantees that your final solution set remains perfectly intact. Moving smoothly onto part two, solving the system. This is where we take those strict rules and actually play the game. This is visual chunking at its absolute best. By stripping away all the distracting elements, the x's, the y's, the plus signs, the equal signs, we experience this massive sense of relief. The chaos is just gone. What we're left with is a clean, highly organized numerical puzzle completely ready to be solved. Every row represents one equation, and that vertical bar simply stands in for the equal sign, holding the boundary between our variables and our final constants. So we solve that puzzle through a highly satisfying process of decluttering, mathematically known as Gaussian elimination. The entire goal here? Force the matrix to literally surrender its hidden answers. We systematically use our allowed row operations to build a sort of staircase. We want leading one stepping down to the right with clean zeros below each of them. This is called row echelon form. Now, if you push the decluttering even further to get zeros above the leading ones too, you reach reduced row echelon form. And at that point, the matrix essentially solves itself.
Keep in mind, when you reduce your matrix, the math will honestly report back one of three possible outcomes. First, you might get a unique solution, where every variable gets one specific, perfect number. Second, you might get no solution. This happens if a row zeroes out entirely on the left side but leaves a number on the right, creating a glaring contradiction, like 0 equals 5, which is obviously impossible. Or, finally, you might get infinitely many solutions. This occurs if an entire row, including the constant, completely turns into zeros. All that means is one of your starting equations was redundant and didn't actually give us any new information.
All right, here comes the big aha moment, where we pivot. We're scaling way up from our sandbox, straight into Section 3, modeling an entire economy.
Notice the massive leap in scale here. It is truly awe-inspiring. We're transitioning from a basic three-variable algebra problem calculating cafeteria sandwiches straight to modeling the 1966 Norwegian economy. Economists successfully mapped out 3,250 interconnected industry sectors. And you want to know the wildest part? They used the exact same matrix engine, the exact same elementary row operations, just on a vastly larger grid. They basically used high school algebra rules to organize millions of data points and understand how every single piece of an entire nation interacted. This incredible scaling didn't just happen overnight. It was a massive paradigm shift sparked by the economist Wassily Leontief. Starting his research way back in 1931, Leontief had a profound realization. He saw that the journey of a physical product through different specialized sectors was exactly like variables in an equation interacting with one another. He understood that a national economy wasn't just this abstract blob of money, but a web of physical dependencies that could be represented by these massive augmented matrices. By mathematically tracking these connections, he laid the entire groundwork for modern intersectoral analysis.
Now, there's a very real challenge here. Trying to map millions of individual products, like every single type of screw, pencil, or microchip, would completely crash the system. It would make the matrix absurdly cumbersome and totally useless. So the brilliance of this model relies on a concept called aggregation. Economists use mathematical formulas to aggregate or group similar products into unified specialized sectors. This ensures that each sector in our giant matrix represents companies using a similar technological procedure, making a massively complex real-world economy actually manageable on paper.
Which brings us to our final stop, Section 4, the input-output table. This is the ultimate real-world form of these economic matrices. So, what is an input-output table? Well, it's simply a giant augmented matrix tailored specifically for economics. It serves as this comprehensive statistical record, showing exactly how much one sector gives to and receives from another. But honestly, it's way more than just a ledger. It reveals the hidden wiring of how a society functions. We aren't just tracking abstract money, we are tracking an intricate, fragile web of physical goods. Stuff like steel, grain, labor, electricity, moving continuously between specialized sectors to keep a nation running.
Take a simplified three-sector economy, for example. You can clearly trace this real-world domino effect just by reading across the rows and down the columns of the data. You can instantly see how a sudden shift in agricultural output immediately impacts the inputs available for the industrial sector. A drought doesn't just mean less wheat, it means factories might actually have to halt operations. This matrix method cuts right through the noise, allowing us to see exactly where bottlenecks might form and how a shock to one isolated sector sends a ripple effect across the entire grid.
Now remember our strict board game rules from earlier? Just like an illegal move destroys our algebra problem, an unbalanced quadrant completely destroys our economic reality. The final input-output table is organically divided into 3 connected quadrants to ensure absolute mathematical balance. Quadrant 1 shows industry-to-industry flows. Quadrant 2 handles final use, like consumer spending. And Quadrant 3 tracks value-added elements like wages and taxes. Every single dollar absolutely must have a home. Because of the strict balance of commodities and money, the global values of these quadrants must perfectly equalize, guaranteeing that every single dollar produced is matched exactly by a dollar consumed or invested.
I'm going to leave you with this one provocative thought to chew on as we wrap up this explainer today. We've seen how a small change in one matrix row literally cascades across a global economy. So if we can truly perfect the math of these giant matrices, aggregating data flawlessly and tracking every single intersectoral dependency in real time, can we foresee and prevent the next massive global economic crisis or supply chain collapse before it even begins? The math is already there. The matrix engine is just waiting to be fired up. Thanks so much for joining me on this deep dive.